We'll give everybody just another minute or two. Others invited. That. Few more trickling in. 6:30 on the dot.
Hi everyone. Good morning, Tom.
Good morning. How are you?
Yeah, I'm good. How are you? It's been long we are talking. Yeah.
That's yes. All right. Get started in a second. Is my screen shared and visible? All right. Thank you for the nods.
Just
One
like
more
a
minute.
real classroom, Tom.
I'm trying hard. I'm reaching way back to my days as I actually spent a year as an adjunct professor at the University of Minnesota. So they they couldn't find anybody else to do it, so they finally got down to me. And I remember I taught a senior class in database theory, and I had like 50 people in the room. It was crazy how big the class was. Um, Grading was really nasty. So anyway, that was my last, I think, formal teaching. But I taught in grad school. Of course, we taught classes all the time. And funny thing, I always thought that professors worked really hard because whenever one sat in on my class, they fell asleep because they must have been so tired from all the work they were doing. So I decided I didn't want to be a professor because obviously they worked so hard that they had to sleep whenever they could. Just turned out that I have a very soothing voice apparently, and a lot of people fall asleep. So don't be too embarrassed. All right, I see we have about 17 people showing up. Good. Um, let's get started with some intro stuff. We're not going to go around the room and do all that stuff. We got too many people, so we'll just launch right into things. Hang on, I got a message. Oh, um, okay. So, app development, and I've kind of conceived this as a bit open-ended. And what I mean by that is I have sort of kind of a syllabus of the first 8 weeks, and we'll talk about that a little bit. But my idea is that this could just sort of continue on forever, in the sense that we can continue to add new ideas and techniques on the end of this. There's a list of 20 more things we could spend a week on each and at least introduce the topics and give you some ideas, let show you some code, show some examples, and just introduce you to new topics. And so I think my idea is for the first 6 8 weeks we'll cover some topics to get everybody kind of on the same page. And after that, if there's interest, we'll start adding on some other things. You know, I've got ideas for RAG. Um, uh, there's all kinds of new models coming out. We can look at models. We can look at the internals of the models. We can learn how to do training. We did a class a few weeks ago with the core India team on how to fine tune a model, and we did some fun stuff with that. So we've got lots of ideas, and so I look at this as sort of a beginning. And today we're going to focus on just getting everybody set up with an environment. Now the assumption is here that you know how to program in Python. A second assumption is you know what an IDE is and that you are familiar with using one because you're going to need that. Probably VS Code. There's other ones that are out there. I'm not going to specify what you need to use. They all work equally well. So the goal for today is just to kind of dip a toe in the water, set some parameters, get you logged into a few different resource areas, and then we'll go from there starting next week. But we'll do a little bit of code today, so don't be too disappointed. Next week we'll start looking at actually querying large language models from Python. So again, the goal of this class is to be able to write a Python app that uses an LLM to do functions. So we'll talk about why we might want to do that and so on. So next week we'll actually, this week we'll do some very simple examples of that. Next week we'll get into some more complicated examples. Third week we'll start talking about frameworks. There's several very popular Python frameworks that abstract out a lot of the details of talking to LLMs. LangChain is one, LlamaIndex is one. There's a new one, or new to me, called DSPY that's from Stanford that looks very interesting. It's a little bit higher level. And so we may do that just because it's kind of neutral territory. Some of the folks have worked with one, LlamaIndex or LangChain or both. So maybe we'll learn a different one. Conceptually a little bit easier, I think, because it's at a little bit of a higher level. It abstracts more of the details away, but it's very interesting and it can do some very, very interesting things. So then once we've sort of introduced ourselves to frameworks, then we'll start building pipelines where we create a multi-step chain using LLMs. An example of that is a year or two ago, I wrote a Python app that generates SQL. Well, first it has to do a step where it understands the natural language question that the user is asking. And to do that, it has some metadata. So it has to read the metadata in. It uses an LLM to process the metadata. Then it formulates a SQL query using another LLM. Then it checks the SQL query to see if the syntax is correct using a third LLM. Then it submits the SQL query to a database. Then it interprets the response and checks to see if there's any errors embedded in that. So it's a 4 or 5 step pipeline that accomplishes one task, but it does it with resilience and it does it with error checking and so on. And I think what you'll find is LLMs are not like functions. They aren't guaranteed to return a deterministic result. So you've got to add some error checking in your pipeline to make sure you're getting back the result that you want. We'll talk about prompt optimization because in a sense, what we're doing is we're writing prompts just like you might do with ChatGPT, but we're controlling it from inside a program environment. So we want to understand how to make our prompts super efficient. And there's some really nice techniques for doing that automate the process and essentially run a bunch of A/B tests against different prompts. So you'll give it a prompt and it'll run hundreds and thousands of tests, altering your prompt slightly in different directions, and then come back with the best prompt for the job. We'll talk about MCP protocol, model control protocol, and the new sort of hot fad of agents. We'll talk about security, how to avoid prompt injection attacks. So I think any of you who have done SQL are probably very well familiar with the idea of SQL injection attacks. Well, there's the idea of prompt injection attacks. And how do we stop people from misusing these cool applications we develop? So if we expose kind of a special purpose chatbot that's supposed to talk about Viore HR policies, how do we stop people from asking it to write pornography or something? And trust me, people, obviously we all know people will do horrible things given the chance. So we want to make sure that nobody can do something despicable, take a screenshot of it and put it on Snapchat and say, look what Viore does. They have this chatbot that generates, Nazi propaganda as something happened to Grok a while ago. So we want to cut that off at the source as much as we can, and there's some really nice ways to do that. Not very many organizations are doing that, unfortunately, but there's a really good one. I think Air Canada just lost a court case where they had a chatbot on their website, and someone uh, sort of jailbroke the chatbot to offer them a coupon for 100% off a flight. And the court said, well, it's your chatbot. It offered it a flight. It's your agent. It's your representative. So you have to honor the coupon. So we want to make sure that we don't create a chatbot, a customer service chatbot that gives away Vuori products for free, things like that. So there's some neat ways to do that. I have in mind that maybe we'll do a little everybody can do a project if they want optionally, and then present that to the class. So that would be sort of the culmination of all this. So again, we assume going into this that you know Python and that you have an IDE that runs Python, and you can do that. I'm going to be using VS Code. You use whatever you like, but that's the assumption. I'm not going to try to teach you Python. I'm not actually a Python expert, so you wouldn't learn very good coding methods from me, but I'll leave that up to you guys to determine how good I am. But I can tell you I'm not the world's best Python programmer, but I know how to get things done with it. All right, so let's see. I guess I'll take a look. Any questions based on that introduction? Anybody want to leave the class because they don't know Python? Anybody too ashamed to leave the class because they don't know Python? Okay, it's okay. You can sit through the class. But I just want to set expectations that I'm not going to teach you Python. Okay. I don't see any hands raised at this point, so I'll continue rolling forward. Okay, so today's agenda, we're going to talk about why we care about AI apps. We'll do a little taxonomy of AI models, so you have a little bit of background. I know not all of you are AI experts. And then we'll get into, let's get our environment set up. Let's look at different ways we can access an AI LLM to use in the class and to use in production, potentially. And then we'll write a little bit of code against those setups so that we understand how to access. And just for Chris, I made sure Grok is included so that we'll be able to access models from Grok in case you're feeling lonely. So why AI apps? So if we think about traditional applications, they tend to be very deterministic. They're great at structured tasks. They handle data in structured ways, and we know how to use them. They can do lots and lots of cool things. They got us to the moon. They're getting us to Mars. All kinds of cool scientific stuff and business stuff and personal stuff. So why would we add AI on top of it? Well, there's a big move towards, I think the biggest move is just having a natural language interface with things. Having to go through a form and pick, check boxes and drop down lists. Why not just be able to type in what we want into a text box? That's the way the world is going. Why not just be able to talk into your mobile phone and tell the app what you want? Why not be able to tell Siri what you want and have it figure out what app to call using AI, then it can tell that app what you want. So using natural language is a huge driver. And in fact, I think a lot of what we see now with chatbots really originated simply from trying to parse natural language. That's where all of this stuff kind of originated, with Google trying to do translation and trying to do natural language. That's where the big breakthroughs in LLMs came. We can also use LLMs to generate original content, document summaries, video summaries. We can generate new pictures. We can use it to create marketing content. We can feed in product specifications and customer reviews and have it generate out of all of that, pick out the important things and generate something kind of new out of that pile of stuff. And I think what you'll find, if you think about it deeply, what are the strengths of LLMs? They have to do with language manipulation, understanding language and or summarizing language and or translating language. Those are kind of the three real big things it does. So if you think about summarization, it really is a translation process. We're going to go from detailed documents to a summary document and 10 bullet points. We're going to go from a scientific textbook to a child's explanation of what's going on. Those are translation tasks, and LLMs are extremely, extremely good at stuff like that. And again, that's partly why they were constructed, was to be able to do stuff like that. Google searches, summarizing the results of searches. Google Translate, translating from one language to another, etc. And then reasoning across information, connecting facts, inferring the intent of the user from their natural language inputs. We can do a lot of that here. And I'm working on an application with Connor right now, which is looking at all the reviews that people have left on the Vuori website and inferring from them any problems that people are mentioning or any particular positives that they're mentioning, so that we can track those over time and see if there's a trend in size or comfort. Is there a positive trend or a negative trend in those? And inferring what people mean out of a statement. When people are typing a quick review, their grammar isn't very good. They make misspellings. They use double negatives. We want to still extract what they mean from that. So inferring their meaning when they're kind of being messy is a great way to use LLMs. So why does this matter for us as app designers? Well, we're trying to help people automate knowledge work, not just repetitive, simple tasks, but enabling people to do these summaries, for example. Great way to enable people to move faster. Excuse me, I'm just getting over a cold. One of the best ways I've found to use AI, and Gemini is really good for this. You don't want to watch a 20-minute YouTube video to fix the carburetor on your car, and you only need one piece of that information. Go to Gemini and have it summarize that YouTube video and just pull out the one piece of information you need. And that is a huge speed up in your life if you're trying to learn something. We can enable natural language interfaces. Our apps can speak to the user. Our users can speak to the apps, and we can understand what they're trying to do, and we can put together apps that respond in natural ways. And we can build features very quickly without having to put in all kinds of cases to handle edge cases. We can let the LLM decide, is this a main case, in which case it goes down our main code path? Is it an edge case? Do we have to do special handling? Do we have to guide the user? Do we need more information from the user? We can again have a conversation with the user without throwing up some nasty error message. And we can fail softer. We can fail in a nice, kind way. We can work with the user. So it just enables an entirely different way of doing things than applications have done in the past. So let's talk about a little bit about history. I'm old, so I like to talk about history because I know a lot of it. I lived through a lot of it. But the AI model evolution really went through basically three phases. The first was really rule-based systems, and that extended from the 50s to the 80s. You can think of a rule-based system as just a really sophisticated bunch of if-then statements. So you just have tons and tons of if-then else statements, and they branch, and there's sophisticated ways to make trees of this stuff. But and you can even start to introduce some some fuzzier logic, some probabilistic branching, and things like that. But at the end of the day, it's a tree of if-then statements. I wrote one of these back in the 80s for, I guess, for eye doctors when they were submitting forms for, I guess, approval for surgery. There was a clear but complicated set of rules that determined whether something would be approved for surgery, for insurance payments or not. And those could be encoded in a set of rules. And I think back then, Texas Instruments was a kind of an AI leader, and they had a pretty sophisticated system where you could encode all these rules and feed them all in. The doctor would answer a couple of questions. The rule would kick out, this is approved, this is not approved, or this is in a gray area, and someone will have to evaluate it by hand. So those dominated. There were some other models that were more natural language. I think if anybody knows the history of computing, they know at MIT they had a thing called ELIZA, which morphed into a program called Doctor, which was a natural language interface that you could sit and talk to, and it played the role of a psychotherapist. And so it had a bunch of it had zero intelligence. There was no neural network. It was template based. So it would start out by saying, "What do you want to talk about today?" And you'd say, "I have a problem with my mother." And it would say, "Tell me about your mother." And you'd say, "My mom is controlling and she manages everything I do." And it would say, "Please go on." And you'd keep typing, and it would say, very interesting. Tell me more. And people got completely sucked in by it. People were sitting in front of this thing doing their own therapy sessions for hours. And this was running on hardware from the 1950s and early 1960s, a PDP-1 at MIT, using a language called Lisp, which I don't think anybody even knows anymore, but we studied in computer science back in the 70s. So it was all template based, but it gave the rough appearance of intelligence. So that was kind of the, sort of the extent. And about that time was the first artificial neuron was described and in mathematical terms, and people started experimenting with it, but the hardware just wasn't there to really implement anything beyond a couple of neurons. So then we go second wave, we get into traditional machine learning. So this is stuff that we're doing, basically all the time now. There's two basic categories: regression, where we're trying to predict, given a set of parameters, we're trying to predict a number. Example would be, how much should a house cost given square footage, number of rooms, and zip code? That's a regression model. We can take 3 inputs and plot that on a line and we learn the line, essentially. We learned how to predict that number. The other basic type is classification. If you're familiar with Silicon Valley, hot dog or not hot dog? Showed a picture, is it a hot dog or not a hot dog? It's a joke within the show, but it's the classical classification problem. Given a set of parameters, is this an okay thing or a not okay thing? You can do binary classification, or you can do multifaceted classification. One of the teachers that I've had, they sort of say you can boil all of AI down to geometry. So regression is a line. You're trying to predict something on a line. Classification is an area. You're trying to draw circles around an area, and something falls into one area or another. So those are the two main things that came out of traditional machine learning. And there's lots of statistical techniques. Most of this is not even considered artificial intelligence currently. At the time, this was like breakthrough stuff. Now it's like, that's just statistics. That's just math. It's not AI. So then we get into the 2010s, and we start to look at breakthroughs in vision processing. The first was CNNs, which are called convolutional neural networks. And convolutions is something you learn in sort of basic AI. It's a mathematical property which has lots of cool things you can do with it. Generally, it applies to matrices of pixels, and convolutions can do things like edge detection uh, and things like that. So uh, stacking neurons that can do convolutional processes on top of each other led to breakthroughs in vision processing. And then recurrent neural networks and long short-term memory networks that allowed for breakthroughs in natural language processing and speech recognition. So we've got all this. Then in about 2017, people at Google wrote a paper called Attention is All You Need. And that was the breakthrough needed to go from speech recognition, speech understanding to production. And we ended up with transformers, which are sequence modeling with language and so on, the ability to predict the next token in a sequence. That's what an LLM does. And diffusion models, which create media, create pictures or video or audio. So they're two very different architectures. So again, we've got our classification models. We predict labels. Look at an email. Is it spam or not spam? Look at a picture. Is it a hot dog or not a hot dog? Look at sentiment. Is it positive or negative? So these are classification. We're predicting a label that would apply to something. Regression is going to predict numbers. Forecasting how much we'll sell next month is a regression problem. They can get arbitrarily complex, they can be linear, they can be nonlinear, etc. But basically, we're predicting a number. And then generative, we're going to create new content or synthesize content. So we're going to translate, summarize, generate text, create images, edit images, etc. So examples of diffusion models. Stable diffusion is something you can run on your laptop. You can download the GitHub and set it up. DALL-E, that's from OpenAI. Midjourney is something you can get on Discord and submit your text, and it'll return an image. A new one, brand new from Google, is Nano Banana. It's actually got an official name, which I think is Gemini 2.5 flash image or something like that, where you just give it a text and it'll generate a picture. And it's very fast and it's very cool and very fun to play with. So the way diffusion models work is they're trained by giving it a picture with associated text. So we say, here's a picture of a dog wearing a spacesuit walking on the surface of the moon. And what we do is we add noise to it all the way until it's pure noise. And the model learns the steps, what happens to the picture as noise is added. Then when we want to generate a picture, we give it text and we give it a noisy background and it reverses the steps. It's very hard to believe almost that this is even possible. But there are plenty of examples. You can go on YouTube and people will walk you through how to write this code. It's actually fairly straightforward. The neural network model is many layers of stuff, but the training process is pretty straightforward and so on. So it's very achievable to do it, especially with small images. Where it gets tricky is having good performance when you've got big images. So then you need some bigger hardware. But this is a very cool thing to do. And if you have some time, go walk through the code. It's kind of amazing. Our other family is generative text models, a little bit easier to understand. And with our class on fine tuning, we went through a lot of the details, a lot of the internal details. But basically, we've got tons of examples of these models. And I've got the example, explain quantum mechanics to a 5-year-old. And so it regurgitates some stuff about a toy car being in your room. So basically, building and training an LLM follows the same basic steps, even as the diffusion model. You collect massive amounts of data, let's say the entire internet plus books plus whatever, all the data you can find, and then you train a baseline model, and the training is pretty straightforward. You give it chunks of text missing the last word, and you ask it to predict the next word in that sequence. And it'll, at first, the neural network is set up and initialized randomly. So it shoots out complete nonsense. And then you say, no, the next word in this sequence is actually this. And what happens is through a process called backpropagation, that that correction is computed mathematically. The difference between what it said the next word would be and what the next word really is calculated mathematically and then back propagated through the entire network. Now, you can imagine this takes a while because these networks, ChatGPT is probably somewhere around a trillion parameters. It takes a while. So to do this training on trillions of words from the internet takes months to train a huge model. I think Llama, one of the meta models that's not too big, 70 billion parameters. I think it's taking like about a month to do a whole training run at a cost of 10 to 20 million dollars. Something like ChatGPT to do a full run, I think the last I heard, and there's no public information, but guesstimates are something on the order of 80 to 100 million dollars to do a full training run. So these guys are and 4 to 8 to 12 weeks of constantly running 100,000 GPUs. So basically, the amount of energy to run a small country to train a new LLM. Now, the good news is that only has to be done basically once for a model, and the inference, the use of the model after that is relatively inexpensive. So all of the expense is in the training side. So now what we have after baseline training, we capture all these patterns, but basically the model really is not very useful. What it does is it predicts the next token. But we then have to do an improvement on top of that. And it's usually reinforcement learning with human feedback is the current technique. That's one thing where we have to teach it. Let's say we have to teach it some manners, I guess. We have to teach it how to respond. We have to show it now. We, instead of just showing it text and what's the next token, we show it a question and what does a good answer look like. And we may do that with, instead of trillions, we may do that with hundreds of thousands of examples. So this is a secondary type of training. And then finally, we can use the model to answer questions. So the training steps are very, very straightforward. We have an untrained LLM, initialized. It's a blob of neurons that are just randomly programmed. They're just assigned random numbers. We do this basic training. We get a base LLM out of that. Then we train it using prompts with desired responses, and now we have what's called an instruction tuned model. Then we may do fine tuning on top of that. So we have a couple different techniques there. So these are like, we want to really improve the prompts. We may want to fine tune a language model to be more fit for a particular purpose. Like maybe we want it to be trained to do scientific work, or maybe we want to train it to find new theorems in math. So we do extra training at this level. So up to three steps, then you can even fine tune beyond that. So this is sort of our pipeline of training. And once we have that, now we have a model that we can use. So once we have a model we can use, there's still further things that we can do. And they fall into three rough categories. We have prompt engineering. That's being, really being clever with prompts and steering the output, steering the behavior of the LLM using wording that we figure out. A really good example of this, and something you can use with ChatGPT or any of the other LLMs, is called few-shot learning. What that means is, now normally, if we have our example on the previous slide, what is the capital of France? That's called zero shot. We just ask it a question and we expect an answer. But if we're asking something more complicated, like we want you to summarize this document, what we might do is give it an example of what we're looking for. So that's called one shot. We can say, here's a document, here's the summary, and I like this summary. Now I want you to do that with this new document. So that's called a one shot. You might have multi-shot or end shot. Let's say we're trying to extract information from the reviews on the Vuori website. We could give it 10 examples. We could say, here's a review, here's the positive thing that I see in it. That's what I want you to do. I want you to extract that. Here's another review. Here's a negative comment. I want you to extract the negative issue. So you could give it 10 examples and then say, okay, here's a real review. Extract the sentiment from it. Extract the problem. LLMs respond extremely well to those sorts of things. So there's a technique you can use today. If you're not getting the results you want, give it an example of what you want. Fine tuning is where it's like we reach inside the brain and we add a new layer of neurons. So these LLMs are layers, and we can go in and add a new layer, and we can train just that layer. We could leave the rest of the LLM alone, and we can train that layer to add new knowledge. So we usually do this if we want to add new behaviors that the LLM doesn't already have. And this is much, much cheaper than training a model from scratch. We said training a new model might be 10 million, $100 million. We could go in and do this fine tuning for just a few $1,000s maybe on a big model. Finally, there's retrieval augmented generation. That's where we use a combination of documents plus what's called semantic search. Example would be, let's say we want to build a chatbot for Vuori's HR department. So we take the entire employee handbook, all of the benefits guides, everything like that, and we just put those in text form, and then we use what's called a semantic database or a vector database. We'll talk about those later, but we can actually take those and break them down into chunks of text that have a key that is the key is a vector that is an encoding of the meaning of the text. Then when a user types in a question, we use the same process to encode their question into a vector that encodes the meaning of their question. And then we can search the database for chunks of text that are close to that. Then we pull that text out, we include it with the prompt, with the question, and we say to the LLM, here's a bunch of text from our manuals that we think is relevant to the user's question. Answer the user's question using only this text. So what does that get us? Well, you may be familiar with the concept of LLMs hallucinating. If we give it text and we say, you have to answer the questions from this text, it will do so, and it won't hallucinate fake answers. So it won't tell people at Vuori that they have 27 weeks of vacation because it thinks that's a good idea for some reason. It'll use the text that we provide, and the semantic search makes sure the text is relevant to the question. So those are three really nice techniques we'll explore later in the course. We probably won't get into fine tuning because we just did a course on that, but maybe down the road. So again, just to summarize, diffusion starts with noise and it generates image, video, or audio. The strengths are audio-visual production and fidelity, but it's really bad. It doesn't do any reasoning, doesn't really do logic. It starts with noise and produces pictures. Very cool, but it's not very useful if you're trying to solve a math problem. LLMs start with a prompt text and generate text output. The strengths are language and reasoning and code generation, because code is just another language, right? So the limits, it doesn't really produce images. So when you go to ChatGPT and you say make an image, it's actually calling a different model. It's using its internal DAL-E system to generate the image. So it may be using the LLM to transform your prompt into a better prompt for image generation, but then it will call a different module for actually producing the image. So, quick pause. Any questions? No? Okay. We'll keep rolling. I'm steamrolling you. So there's no questions because you're so in awe of all this information. Great. Okay, so let's talk about local versus cloud LLM. So I'm sure everybody's used ChatGPT, Grok, Anthropic, whatever. Those are frontier models. Frontier models are those that are on the cutting edge. The biggest models, they have to be run in a giant data center. They're too big to run on your laptop. And generally, they're very scalable. They spend huge amounts of resources making them scalable, reusable, etc. Um, and they're generally pay for a subscription. Many of them have free tiers. The APIs are typically pay by the token. So you know, we're going to talk about some that have some free levels that you can use for this class. So my goal is not to bankrupt you with API calling fees. I've got 3 or 4 that you can use for free, at least up to a certain point. But I really like using local models. It depends on what hardware you have available, what you're allowed to install on your laptop, etc. But there's lots and lots of local models that range from ones that are so small they'll run on your phone to ones that'll run on a decent sized laptop. They may require GPUs, they may not. It's a fun way to experiment. Many of them are released by the big guys, but they're smaller versions. OpenAI recently released GPT OSS, a 20 billion parameter and 120 billion parameter model. Meta has released many. Grok just released one, although it's still probably too big to run on anything reasonable. So we'll part of today, we're going to look at setting up to run locally, but we'll also look at how to access these in the cloud. So with that, we'll launch into setting up our local thing. And again, we're recording this, and I'm going to put out a GitHub to the group so that you'll be able to download all this information, including the slide presentation. You won't have to guess at this. So let me, I'm just going to switch over to a different screen. We'll go to, oops, wait a minute. Okay, there we go. All right, so we'll go to LM Studio. And it's this easy. Whatever machine you're on, it will just give you this download, and you do a typical download and install. I already have it on my machine, so I'm not going to go through that process, but it's very straightforward. So let me switch over to what the interface looks like. And it's kind of an all-in-one type of interface. It's got a chat bot so you can talk directly to LLMs. It's got a server so that we can access it via an API. It's got here's all the models. And then if you want to download a model, it's got a search function. So you can look for models on, basically the next step we'll talk about where the models live, but there's a place called Hugging Face, which is the hub for all models. But for now, we'll use a model that I already have downloaded, and it just give you some ideas of, kind of what's going on. So here's a really tiny model. This is from Meta. It's called Llama 3.2, and it's 1 billion parameters. Okay, so if I go to my chatbot, I can say load that one. And so it loads it, and now we can talk to it. And so you get an interface just like ChatGPT. So we can say something like, explain quantum mechanics like I'm 8 years old. It's very fast. It's very small and very fast. And it gives you kind of a reasonable explanation. This is a very tiny model. But if I ask it something obscure, so I'll reach into my memory banks and I'll say, who were the Coneheads? Now, I'm expecting most of you not to even know what this means, but so the Coneheads there's a show in the US called Saturday Night Live, and it's been on the air for 50 years. And in the first seasons, so 50 years ago, they had some skits about these aliens who are called the Coneheads. And they were very famous. It's a big cultural thing. But I wouldn't expect anybody that wasn't born 40, 50 years ago to even know who they are. But you could see this model is just absolutely making this up. They were an American rock band from New York City, formed in 1963. Absolutely false. Absolutely untrue. So why is this? Well, number one, couple things. We have the temperature is set to 0.8. So temperature allows the model to be more to select next tokens that are less likely in probability, I guess. If we set the temperature down low, I guess I haven't really tried this, but we'll experiment with that in a minute. I don't want to get off track, but think about a model. If you take the entire internet and compress it down to 1 billion bytes of information, it's going to be lossy. Think about that. Let's say the internet is 8 trillion words. We're going to try to compress that down to 1 billion. We're going to lose some information in the process. It's just that's just the way the world works. So these small models are going to just not know this obscure stuff. Quantum mechanics, there's lots of references through the internet about quantum mechanics. The Coneheads, not so much. So we can go up a model size or two. So maybe we go to Qwen 4B. So now we're at a 4 billion model. And just to be fair, I'll start a brand new chat, make sure it doesn't have any previous context. And we'll ask, who are the Coneheads here? The Coneheads are a pejorative slang term describing people with, with conically shaped heads. Again, it's just totally false. It's making this up. If we go up another model size, let's say Gemma 12B, so now this is 12 times the size of the first model we tried. See, it takes a little bit longer to load. Takes a little bit longer to think. Oh, here we go. A recurring sketch comedy on Saturday Night Live, briefly revised. They're aliens. It has the who were the stars, who made them memorable. I mean, that is so we had to go up to a 12 billion parameter model to get a good answer for this obscure question. So I just want to illustrate the fact that really creating these models is an exercise in compression. Think about a model as compressing all the information you give it into a small area. If it's too small, it's going to lose information. If it's too big, you'll train and train and train and train, and the parameters never quite converge. So model size will dictate how much information you need to train it properly and how much information it can hold. So it's a fine line between information containment and information training. So kind of an interesting thing. So the other thing we have here, I'm sorry. Let me go back to my slide so I don't get. Otherwise, I'll end up getting off track, and nobody wants that. All right, so that's setting up LM Studio. So let's talk about models. Models are on Hugging Face, and I want to talk a little bit about model nomenclature. So I'm going to pop ahead a little bit. I want to tell you about what the names of the models are going to mean, and that'll help us find some interesting models. So here's a little bit of a cheat sheet I put together, and the model names will be things like Llama 3-170B Versatile, Mixtral 8x7B 32768, etc. So what do all these little things mean? Well, remember we had the base model, so that gives us a raw model. We have an instruct, if it says instruct, chat, or IT, it means it's been tuned to follow instructions. If it says reasoning, it means it's a thinking model and it'll do deep thinking. It may say reasoning, thinking, etc. If we have an MOE, it's a architecture that supports, it's actually multiple models inside of a container, and it has a router on the front of it that will activate certain experts, certain models inside based on the prompt. If it's quantized, which means it's compressed even further, it'll indicate like a Q4, meaning it's 4-bit quantization. We'll talk more about that later. We'll have VL, or VLM. That means it's a vision model, which means you can input pictures and it will understand them. If it says coder, it means it's tuned to write code, the size in billions of parameters, and then context. How many tokens can it handle in one input? It used to be 4,000 was big. Now a lot of models will handle 1 million tokens. That's important if you want to do retrieval augmented generation and things like that. So we'll pop over to Hugging Face, and to use with LM Studio, you want to find ones that are they've been instruction tuned, and they have a version that's called a GGUF. And you can easily search for this. If you're on a Mac, you can also use MLX models. It's just that LM Studio happens to work best with these models that have been formatted in this particular way. Then you can download them and import them into LM Studio, and then you can start it up. So I've already got LM Studio running. You can go to Hugging Face and set up your own account. It's free. And they also provide models on there, and I'll show you that in a minute. I'm running a little bit long on time here, so I'm going to try to hustle through the last couple slides. We're almost there. Let me just get LM Studio back. So if we go here, this spyglass or magnifying glass, we can search for models. So if we're interested in a particular model, like a Llama model, first right off the bat, you see Llama 3.2, that's the version. It's 3 billion parameters, it's instruction tuned, and it's a GGUF. And over here, you'll see a lot of statistics, some commentary, technical details, when it was last updated. And here you can do a download, and it says it's going to be 2 gigabytes. So you just hit the download, and that'll start downloading right into your LM Studio. Keep in mind, these are pretty big. You know, some of these models can be 50 gigabytes. You have, and if you're going to download a model that's LM Studio is kind of aware of your environment. So it'll give you a flag. It'll say this model probably won't run in your environment because it's too big. So a 3 billion parameter model, again, this is quantized. You can see this Q4KM is an indication of how compressed it is. So Q4, no, the normal is 16-bit. So Q4 means it's 1/4 the size. So right now we can load the model. We have 3.23b loaded. We can now chat with it. So we can, go back to our. So this actually is, there was a film that was made of the cone heads. So, there's some truth to this one. I don't know the film very well, so I can't verify that this is true, but I know that they were from the planet Remulac. So this is at least a basically true answer, and we're at a 3 billion parameter model, so that's pretty small. So that's how you download a model real quickly into LM Studio, and that's coming from Hugging Face. And if you go to the Hugging Face website, there are hundreds of thousands of models in here. Most of them are fine tunes. And they're broken into communities. So for people on Macs, there's an MLX community full of models that are tuned for Macs. You can go to the Llama Meta Llama community. So Meta Llama has the whole family of Meta models, and so they have Llama 4, and there's, again, you can see Llama 4, Scout, 17B, 16E, Instruct, etc. Stuff that I just kind of went over that terminology. So you can go on here and explore. One cool thing is if you pick a model, one side note on meta models, you have to register. It's like you have to register your email with Llama and be approved to download their models. There are licensing. Some of these are completely open source. You can use them for anything. Llama models are like, you can use them for anything up to 1 million users. Then you have to contact them for a commercial license. So you have to be a little bit careful. If you're going to build an app, you have to pay attention to the licensing. Is this allowed for commercial use? Is it for personal use only, etc.? So you can explore that on your own. And that. So here's a little thing on quantization. I'll let you read that on your own. It's not that interesting. We looked at different models, already did that. So now we can get into a little bit more fun stuff where we'll do a little tiny bit of code writing to end the morning. Got to end with some code, right? Where is my, there we go. Okay, so here's a code snippet. Give me a nod if you can actually read it or if I need to zoom in on it a little bit. Is it readable? Okay. Just make it a little better. Okay. So here's our first code snippet here. we're gonna go against our LM Studio, and we just need to. These are just requests is just an HTTP thing. This notebook thing, it's not really needed in this thing, but there's something else that complains about it if I don't have it in later. So let me just pop back over to LM Studio, and I'll show you the server part. So right here, this kind of funny little box here. So here's the server. The important thing is there's no model loaded right now. So you can preload a model, or you can let the call load it. It'll just cause a delay. The important thing though is you want it to be running, and you want to see what address it's reachable at. So you can just copy that. It tells you, what model it's probably loaded last, etc. So we can then pop back over to our code. And you can see right here in the URL, I have exactly that. And what I've added is V1 chat completions. That's a standard OpenAI protocol. That's an endpoint for the server. That's who we're going to be talking to. So then we set up a payload, which is just a JSON object. And we say, what model do we want to use? We then give it two messages. We give it a system message, which kind of gives it some context. We tell you're a helpful physics professor and a YouTube presenter that excels in explaining science to kids. And then we give it a user message, which is what we would be typing into the prompt box. Explain like I'm 10 quantum mechanics. We can set a limit on how many tokens it will return, and we can set a temperature, which again controls the randomness of the response, the creativity of the response. The higher the temperature, the more creativity the response will have. But if it's too high, then it can start to hallucinate. And then we have a very, very straightforward, if you're used to any kind of, post get type of programming with URLs, we get a response. We post the payload to the URL. We get a response, and we print it out. So let's run that. Now while it's running, I'll pop back over, and we'll look at the server, what's going on at the server. It's running. You can see it's running a chat completion on the conversation. Remember, we sent two messages. We sent a system message and a user message. It's running OpenAI GPT OSS 20B. It thought for 0.22 seconds. So now we'll go back and see what we have. And it's still running, I believe. Here we go. All right, here's our answer. Sorry, it just scrolled down. Welcome to Quantum Mechanics for Kids, the easiest way to understand the weirdest part of physics. One thing you'll notice, this is actually a really nice markdown format. So you could actually, copy and paste this, copy the cell output, put it in a new document. We'll call the document, something markdown, and it would be a really nicely formatted document. So that's our first use of the LM Studio as a server. And we can do the same thing. Now, what I want to do is just show you one or two alternatives, and then we'll call it a day. But if you can't use LM Studio on your laptop, if you have a Viori laptop, maybe you can't install this. If you have no memory, maybe it won't run. You can use free resources on the internet. So Hugging Face hosts many of these models and gives you some free allowance. So Here's a piece of code that will do exactly what I just did, except it uses Hugging Face. So you'll notice the base URL, instead of being our local model, it's using huggingface.co. And here's the answer coming. Otherwise, everything else basically is the same. The format, the model, I'm using the same model. I'm using the same system and user prompts, same everything, but the response will probably be a little bit different because there is some randomness. There's another system called Open Router that allows you access to thousands of models. Not all of them are free, but some of them are. So I chose a model called DeepSeek Chat 3.1 free. Again, if I run this, it's going to call Open Router and do exactly the same thing. Same format, same messages, etc. And here's its answer. It's a different model. Here's Grok. If you sign up at Grok, you get a bunch of free credits. I don't think you can use the Grok model for free, but they do have, so here's Meta's Llama 3.1 that's hosted at Grok. You can use that. And it's very fast. It's a tiny model running in a big data center, so it's very fast. Here's an example using Google Gemini. And they use a slightly different format. So I'll put this in the GitHub. I'll send everybody the GitHub access, and you'll be able to download this. The only trick is that all of these require an API key, and they're easy to do. So the last thing I'll show before I let everybody go, sorry for running long. If we go back to our Hugging Face, when you set up an account, you can go to access tokens. And you can say, create a new token. And we'll just do a read token. It's easy. It gives you a token that looks like this. You copy that over. And I set up a .env file. And what this does is it reads the API key out of that .env file. So it just looks like this. It has all these. I expire these every day. So these don't copy these because they won't work. The next thing I do after class will be to go delete these. But when you set up an HF token, you just set up HF token equals that one I just put in, and that allows you to log in. So that is pretty much what I wanted to cover today. I'm happy to hang around and answer any questions that anybody has. But I know we're over by about 9 minutes, so that's actually pretty good for me, as the India team knows. So like I said, feel free to go. I'll post access to the GitHub, which will have the slides and the sample code notebook, so that you can try all this stuff on your own before next week. So that's kind of the homework. Get everything set up and working. Ask any questions. If you can't get things working, we'll work through it. And then next week we'll move on to more sophisticated stuff. So let me know if you have any questions. Either raise your hand, either ask them out loud, or shoot them in text.
Appreciate it, Tom.
My pleasure. My pleasure. Have a great day, everybody.
Bye. Thank you, Tom.
Thank you, Tom.
Bye.
Thank you, Tom. Bye.
Thank you, everyone.
Bye, Tom. Bye, everyone.
Thank you.
Thank you, everyone. Thank you, everyone.